Thank you so much. Good afternoon, everyone. Welcome to another episode of AI Plus Seminars, another talk, I should say, as part of the UQ AI Collaboratory. So let me first acknowledge the country. So UQ acknowledges the traditional owners and their custodianship of the lands on which we meet. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognize their valuable contributions to Australian and global society. So for those who are not quite familiar with this seminar series, this AI Plus seminar series is supposed to promote interdisciplinary research with a focus on AI. In particular, with the aim of establishing connection between UQ-AI researchers and students, and also, as the talk here suggests, with also a particular focus on the application areas and the areas that AI has had recent impacts, in particular, agriculture, health, and energy. And in the sector of agriculture, we have had one talk already in March by Professor Chapman, who's also a colleague of mine and Andries. Today, we're going to be hearing from Associate Professor Andries Potgieter, and there's another talk in the same sort of the realm of agriculture coming up in May, which you can see on the screen. Now, I don't, they gave me these slides, they put my name and face on there, so I guess I gotta introduce myself. So my name is Fred, and I am a senior lecturer from the School of Math and Physics, and I do also research in AI and machine learning, in particular on the theoretical aspects, but I'm also very interested in the application. I got to know Andries a few years ago, and we sort of hit it off, and we have been involved on so many fronts in terms of grants and co-supervision and joint projects and so on. So we have had a very close relationship, I guess, from 2018. Now, Andries is an associate professor and a principal research fellow at the Queensland Alliance for Agriculture and Food Innovation at UQ. And he's got actually quite a large team, because he's currently working on several different projects. And the main focus of these projects are on seasonal climate forecasting, remote and sort of proximal sensing, with a lot of applications, in particular in terms of crop production outlooks, and also developing sort of a cropping systems with less risk across Australia. So without further ado, I'll invite you to the talk by Andries. Andries, please take it away.
Thank you, Fred. My talk today, as I said, will be about how we can use these technologies to better improve our decisions, but also specifically increase our production at a specific scale. And I'm privileged to work with a big team and many people in UQ and nationally and also internationally. In the next hour, I'll go and look back a bit, look back first before we can move forward in terms of facing the future, touch base on that. Also go through farming systems, specifically where 60 years ago, when I grew up, and how that has changed to today. Touch base on climate variability and change, the challenges that then cause for food production, both nationally and globally. The use of integrated approaches to help us find better solutions, and then go into examples, and then new frontiers in digital ag. I find the Dreamtime story of Like the Frog very fascinating in terms of it's been told by for thousands of years by the Awabakal Aboriginal people in Australia, and mainly the story about Like the Frog is about droughts and floods, and that is that is, as you all know, Australia is highly impacted by that, but also globally it happens. But this story has been 1,000 years, been more than 1,000 years, thousands of years been told by many dialects of the Aboriginal people. In short, the Tiddalak the frog was in drought years thirsty and drank all the water. All the animals came together and tried to, get the water back to make it rain again. And what happened is that at the end, the dancing snake made him laugh, and he brought all the water back up again. So that's a very simple story, but in my work, and I find that very, very interesting that in that simple story, there's a lot of lessons and symbologies that we can glean from that. Specifically, how as human beings are interacting with the environment that we live, that's around us, how we manage that. And also, as human beings, we have to observe what's around us, and then take that observations and build solutions around that. This will then help to mitigate and prevent the impact of future climates. By ignoring these signs, by ignoring Tiddalak, it can have huge consequences and huge impact, negative impact on climate. As I said, I grew up in South Africa. 60 years ago, I wasn't born then though, but I remember my father as a young kid, going through all the struggles, working the land. Planning was done on a map by drawing it. Cropping systems, taking notes was just in a book. Cropping those times was also highly impacted and still are highly impacted by climate. Remember the droughts of the 80s, the 90s, and there's teleconnections between different countries, and there's between the rainfall and the rainfall variability. So the globe is connected. Energy moves around this continent of ours and this globe of ours. Farming was those days opportunistic, very opportunistic. Planting and sowing would have occurred over 2 or 3 months due to the hard labor. And if it rains, then you decide to plant. Moving on, 60 years forward and up to today, sowing can happen with, thousands of hectares can be sown and harvested within basically 12 to 24 hours. Farming practices has changed. There's also decision tools that help better inform producers to make more informed decisions. And it's also about timing of those, that information systems. So one of the biggest challenges we have today is, it's one thing to say, I can predict a certain trade accurately, but how early can you predict that trade to be better informed? And we're moving into, Industry 5.0 with robots, fully automated, autonomous vehicles on the farm. So very exciting future ahead. The last 100 years, 120 years, you look at the slide, unraveling the different underlying trends of climate variability per se and climate change. So there's an annual, decadal, and interannual variability trend, but there's also a long-term change. And if you can look at this diagram for a few seconds, it goes around on the outer circle is just the months, the temporal, and this is depicting the global temperatures from the early 1800s, late 1800s to now. And as you can see, we've reached about in the 40s, 50s, it's creeping around 0 degrees Celsius. And then it goes up during the late 70s. You will start seeing that it consistently will go above the 0 degree and the anomaly of global sea surface temperatures. And it's moving away from the bullseye. And that is, it's putting us, making us more and more challenging actually farming per se and producing food, enough food. And as you can see, it went from a bullseye to this type of funnel. And it is now touching or going beyond the 1 degree change. So climate, you've seen the climate, the variability in that, the change, that produces or creates a lot of challenges for farming systems per se, and also for global food production. So the current yield trends, for example, are insufficient to double a crop by 2050. It's predicted that we are traveling now about 1.6%. We need about it to grow. The global trend in crops, food production, in yield needs to grow about 2.4%. And there's different challenges around that. So we need significant advances in productivity to actually meet this demand, global demand. Coming closer to Australia, when you look at that, this, the wheat crop is the main winter crop in Australia, cereal crop, one of the main commodities, or the main commodity for winter cropping in Australia. Sorghum is the main summer crop in Australia, which wheat is produced across Australia. Sorghum is produced just in northeastern Australia mainly. Australia crop yields are although not increasing, they still need to advance even further. And there you can see the trend in sorghum crops from 1983, the last 40 years, was about traveling around 1.67%, 1.6% per year. For wheat, that was about 1.5%. But when we remove the impact or the signal, when we account for the climate, the impact of climate on that trend, the story looks a little slightly different, and you can see that sorghum is slightly reduced to 1.49 or 1.5% annual trend when you remove the signal of the impact of climate. But wheat, is nearly half that. So the challenges are there. Yield is a function of the genotype by environment, by management, and impacts across the supply chain. Production is a function then of market. So what are the producers getting for producing a ton of wheat, for instance, or a ton of sorghum? What are they paid? What's the profitability at the end? So we at UQ have developed integrated systems approaches to derive novel solutions to enhance these productivity and through better informing both at temporal and spatial scales. Looking back again from the 18th century, we're going through the industrial revolutions. We're sitting with cyber physical production systems. We're sitting now around Industry 4.0. Currently, today, these are mainly digital technologies that play a critical part in enhancing production and profitability. These include things like dynamic crop models, drones, UAVs, machine learning approaches, smart deep learning approaches from mathematics and statistics, and earth observation, remote sensing. And there's a lot of new, and I won't touch on that here today in my talk, but there's a lot of new satellites that's already launched and planned to be launched, specifically targeting the agricultural and measuring how a crop is experiencing the current climate. As I mentioned, at UQ, we've developed integrated approaches across the scales, using, from cell, leaf, plant, plot, through the canopy to field and regional level. We use different sensing equipment or platforms for that, from microscopes in the lab, IoTs in the field. As you can see there, a cyber physical technology we use, and then up to UAVs, satellites, and airplanes. And these are specifically used then to find solutions to how to measure a specific trait of the current or of a crop in a specific location. But then also, once we find that trait in terms of, say, crop stress or photosynthesis or radio use efficiency, how can you then use that to better inform and improve the system? But also, is it possible then to use it in breeding program to select and faster select certain traits that has not been seen or can't be seen by the human eye. So that's a space that agriculture is moving in and fast moving in. Now, in the next few slides, I will go through a few examples of the work I'm involved in and just highlight some of the outputs on that. So the first one is a project, GRDC funded project, that's basically the target there is to better map crop phenology and more accurately crop type discrimination. This project, the main reason for this is to optimize risk or input cost, manage the risk that across both at a farm level, but in a field scale, but also regional scales, and improve whole farm profitability. So this is just the slide to show you that part of this is we have all these validation sites across Australia, you know, from northeastern Australia near to Woomba, where we plant different genotypes, different crops, South Australia, Carlington, and Western Australia, Dale. And we use the same sensors, the same protocols. We fly all of them. We have fixed cameras in the field, and then also fly the latest Ultim MicaSense multi-spec camera, which is important because it's narrow band and also can detect temperature, which is important for the synthesis and tomato conductance measurements. Data that we use, our commercial partner is Data Farming. And yeah, please, if you are interested in Data Farming's platform, just go to their website. Very intuitive and easy to use website for bringing satellite Earth observation data to you as client. We use thousands, hundreds of thousands of samples for each crop type from Data Farming. Each sample there is about 10 meter, so 10 by 10 meter. And we have that for different crops, barley, chickpea, wheat, oats, canola, lentils. So as deep learning or mathematicians, you know, when they see that type of data, they get excited because it's a big data set. So that's challenges around that too. But we then measure phenology across these validation sites, but also a national survey through Data Farming that we then measure certain stages of phenology, like flowering and tillering, which is important stages of phenology, but we also use that then to train a crop ID model to discriminate accurately between these crops across the whole of Australia. This is an example of the Ultim camera I mentioned. You get a spatial map of each pixel, which pixel is there about 1 centimeter, of a vegetation index from this camera on the left-hand side, and on the right-hand side in the middle is the temperature. But we extract then the temperature on the canopy. And the temporal figures there is just showing you the index that we used. And then on the bottom right-hand side, you can see the canopy temperature is much higher in the total when you include soil. But when you just look at the way a crop is experiencing temperature at that moment in time, the temperature due to transpiration, the canopy cools down a bit. So the temperatures are much lower. We do this for all sites and analyze that then. So we also have the temporal profiles across these sites from these cameras, where we then observe phenology stages and obviously do further analysis, and also develop using mathematical algorithms to accurately map these phenology stages from remote sensing. That's the work that Dr. Jan Zhao from UQ is doing, mathematical derivatives. From this is an example of a sorghum profile. And this is from a Sentinel platform, not a UAV. And you can see the different dates that we have data for, different description of each stage, and then use these mathematical approaches then to then align that with things like stages like flowering and tillering, start of season, end of season. Dr. Jan Zhao is working on that, and we hope to be in the near future to map larger regions of say flowering. As an example, so this is just a shire in northern New South Wales, Moree Shire, where we actually, use these mathematical approaches and then map every pixel at a 10-meter pixel scale across the region, but also within a farm and a field. We can then map for different crops the flowering dates, for instance, based on the analysis we did using this data. So the other aspect from this project, CropFen, is using AI to determine crop type. This is work it's led by Dung and Jan again. And again, we use the data farming data fields that I showed you before. The long short-term memory model, also with Fred's Roesta's help in this, we use that approach. Dung has developed that, and we now has just managed to run and calibrate, develop a deep learning model across all 17 regions, GRDC regions, as you can see on the map of Australia there. There's different colors, but each of those polygons basically represents an agroecological zone in Australia. So we will then take this. It shows very high accuracy for both across crops. Barley and wheat is above 90, close to 95% in user accuracy, as well as correctly classifies even higher. Then we look at these regions, and it gets correctly classified close to above 95% for all regions. So as soon as you have, if you instead of averaging, you go to each region and you look at those accuracies, and this is using 70% of all those hundreds and thousands of samples to train the model on, and then predict the other, or test the model on the other 30% of that. So very good. There's still some challenges. We've done some analysis on that. So to avoid spatial coherence or spatial autocorrelation in terms of accuracy, and we find that the accuracy drop about 5% when you go from a pixel to a field scale. Actually, when you use that approach, but then at a field scale, when you aggregate to a field scale, the accuracy goes up again. So another work that I've been involved in for more than 25, 30 years, and specifically this work has started with Professor Graham Hammer at UQ 23 years ago. And we've developed, we have a different approach in terms of just, a black box. Graham and Professor Scott Chapman, and they were all involved in developing a very dynamic model for crop growth. This model that I'm using here is not a point scale dynamic model. It's a very simplified model, but it accounts for the way a crop is seeing the environment and rainfall and climate and temperatures per se. So we've been doing this work for the last 23 years, predicting the yield across time, across Australia for a wheat crop and a sorghum crop. In the last 10, 15 years, on the top right-hand side there, you can see calculating of areas for specific crops like wheat, barley, chickpea for northeastern Australia. And that work I've been done from 2003 onwards to 2020. And that has then eventuated now into CropFen and taking this further. But yeah, so the aspect of utility, I mentioned, early on, how early on can you actually predict something accurately, and how accurate can you predict that? That aspect is critical, but also the other aspect about any forecasting system is to look at the overall trend. Is if you can follow if it's going down or up over time, then you can make more informed. So that the temporal aspect of any system is just as important as attribute as the specific accuracy. I was also involved with people from the States. I think Stanford University, Professor Gu and Lobel, where we actually, instead of using a biophysical model, we just use purely climate and also remote sensing. So we integrated that, but they've used and applied their the machine learning approaches to that across Australia at a higher level. But we also included the solar-induced fluorescence satellite. So solar-induced fluorescence is actually is basically measuring crop stress, but at a cell level, which is very important when you talk about abiotic and biotic stresses, when you want to measure that. And you can see also the temporal aspect of that. Early on, up to August, it's not that not that accurate, but then around October, full canopy, the accuracy gets higher. But compared to the biophysical model, this is slightly more challenging. It's not as accurate because it doesn't take into account the way a crop is actually experiencing, or a plant is experiencing the climate, crop growth, and it's not integrating or counting for the way a plant is seeing the environment. Another project I'm involved in, and Fred is involved in this, the CI, is ARC linkage project, where we actually then, as I mentioned, utility, timing of crops, but then integrating and fusing this biophysical model with our remote sensing model. And then additional to this, we then use the global climate model. The global climate model, Bureau of Meteorology has developed the Access S, and now Access S2. I'm working with Dr. Andries from CSIRO on this, using his global climate model downscaling. And we just submitted a paper on that. That work basically is to see what's the skill in GCMs across Australia, not just at one point location, but across Australia for predicting wheat yield. But how early can we predict that? So can we actually predict wheat yield and with some accuracy early on before the crop is even planted? So that's very critical. So that will be the next big step, is how far ahead of time can you actually predict with some accuracy that's just better than flipping a coin, 50-50. Yeah. Applications again, when we have the crop type from CropFin classification, again in Maurice area, and then we predict the yield, which is, we publish that work on yield prediction at the 10-meter pixel scale across Australia, very accurately now for wheat yield. And when you combine that with the GCM forecast, as I mentioned before, we've submitted this paper now on predicting it yields at 17 shires across Australia. The Crop Vision project is about 36 shires, which covers about 60% of the total production of Australian wheat crop. The way this works in an operational sense, on the top right-hand side, we do a probabilistic forecast. We don't give an absolute number. So we run the model every day, the GCM model, and then the GCM is that climate, drives the climate into the biophysical model. And then at sowing, dynamic sowing, we project forward based on the ensembles from the GCM. And that ensemble becomes your forecast distribution. And at the bottom there, you can see the example of just for 1 year, for instance, 1998, which was a very wet year, and how early on the GCM at March could have predicted that. And that the GCM forecast is the orange. And you can see from the start, the GCM already was above the long-term median line, which is the black dotted line there. While climatology was below that, which is the reference, and the analog system was just also below that. So yeah, definitely potential. We just finalized that work now and submitted it for a paper to be published. This is crop vision, or the work. So this GCM again, just showing that in each shire we use, you use all the climate stations. At the bottom left-hand side there, the blue, and there's 2 shires, one in Western Australia and one in Northeastern Australia. And the shift that we see in the GCM yield forecast using the GCM connected to our biophysical model is more than 2 months ahead of sowing. So, and also one more very important aspect here in this downscaling a GCM is not trivial. And Andries has developed some smart Bayesian approaches to actually publish that, to actually include the spatial and temporal aspects of, and through a mathematical approach, a statistical approach, to actually remove the bias of these systems. So GCMs, they give ensemble or forecast about 50 kilometer by 50 kilometer grids. So actually to then use that forecast at the climate station level, where the crop model is running at, you need to remove the bias of that system. And that's very important in any linking of any global climate model to any crop model. As I mentioned, the yield forecast model, we developed a model that uses the structural from remote sensing, the structural aspects of canopy, the chlorophyll aspect, which is related to photosynthesis and canopy health. And then there's an example, a published paper there you can follow up on or read. And we get over 90% R-square and very low root mean square error across 100 fields for 2 years in northeastern Australia. We applied it also to a lot of other points across Australia, and those accuracies are slightly lower because those points only came from a radius of 10 meters around the point. We couldn't get the field data. In the crop vision, we have new surveys happening, and we will recalibrate this model and update it to be more accurate across Australia. This is an example of the pixel scale yield tons per hectare for wheat in Moree for the 2020 season. And then in between that, we convert that to, we get an area of that and we convert that to a 5K by 5K grid point cell production. That's an example, which is part of a project. This data then goes into the supply chain project, digital supply chain, Professor Scott Chapman led at here at UQ. And you can see the top is the area. We actually, crop vision creates this as each 10-meter pixel scale, with crop fin involved in that. The yield for the last 5 years at each of those grids. And then we have the production, how much volume, which is then feed into the grain supply chain digital twin, but also an output, specifically an output of crop vision. Example at the farm scale and the field scale, you can see the yield there. Again, wheat yield, and you can see the phenology, and then also remote sensing, earth observation, looking at soil moisture becomes a very important layer for decision making. Other work we have just now finalized is an automated approach to actually detect crop intensity from Sentinel, which is a 10-meter by 10-meter satellite. And there you can see an example on the left-hand side of the fallow land and cropping land. But then also on the right-hand side, there's 2 farms there. And when validating that, you can see the crop intensity, the red, only one crop in the last 6 years, while the blue, the orange goes up to 4 crops in the last 6 years. And it was 2 or 3 years of those last 6 years was very dry. That's that. Okay. How do we take all of this data? We convert it into information, and not only temporal but also spatially. Very important. So we start with the climate. We then add the soil moisture, the canopy structure from remote sensing, the chlorophyll from remote sensing. We add the biophysical rigor around this, because it's very important for cropping and even pastures to add biophysical rigor around any model, so that it's not just a black box. We then produce these outputs at the pixel scale, at the field scale. You can then apply zoning to that, and then that will help to optimize input costs across the farm, manage the risk better in season, and therefore improve whole farm profitability. I mentioned the grain supply chain digital twin. It's led by Professor Scott Chapman and also myself and Professor Reinko and others in SAFS, Adam and Julius. I won't go into too much detail about that. I think Scott has already talked about it and probably can talk about it later on. Other work I've been involved in 2016, we built this, the Gecko platform, the tractor you see on the top left photo there. I led that work, building that sensors within the David Jordan, Graham Hammer, and Scott Chapman, the COE center. And we have UAVs flying that mainly on sorghum. This was mainly on sorghum. That tractor is now used also on wheat, both Gatton and at Hermitage. We've developed this phenotyping pipeline, software pipeline. So phenomics to better inform us in terms of what traits we are targeting from remote sensing. These tractors and UAVs, as I said, is got lots of sensors on them. We then extract that. We have observations on the ground. We calibrate that. And then predict other traits across thousands of plots, and then determine what's the heritability of that trait from remote sensing, from sensing. Example there, another example we published is just simple, detecting number of plants in a plot. Each of these plots is about 6 meters by 3 meters. For sorghum, number of plants, number of heads, sorghum heads, and tillers. And then the tillering in a sorghum plant, if you don't know a sorghum plant, is becomes a trait that's of interest to breeders. So we've published this work, and we can actually determine number of tillers on the top right-hand side. You can see that image across large fields from just UAV data, which becomes very important for breeders. Now, the new frontiers in utilizing AI, because this is an AI session, seminar, and then specifically also sensing in agriculture is, recapturing that is crop phenology, crop type, the photosynthesis. I haven't talked much about that. The fluorescence and crop stress is becoming a very, very important trait and becoming more challenging for these systems. Then the fusion of AI and digital technologies through and crop models through deep learning becomes very, very critical and important. Use the number of data points we are using. And as I mentioned, we're moving, there's a bottom left, there's a fields in Victoria, few cropping fields for wheat, barley, lentils, canola. And that's an example of a new Prisma Italian satellite at 30 meter by 30 meter pixel scale with 200 and close to 300 wavelength bands across the whole electromagnetic spectrum. So we're utilizing that satellite, but we're also working with University of Melbourne, flying their plane with hyperspectral cameras and temperature cameras. So there's more to come in that space, and then measuring crop type, crop phenology, but also crop stress through solar-induced fluorescence. The last slide here is just to say that we are advances, these technologies, by integrating these technologies, can become disruptive and will become disruptive technologies in future. It's predicted that farming tech is the core to deliver 70% increase in global crop production. So my talk's about food production, but applying farming tech, the prediction is by 70% increase in global crop production by utilizing not only all farming tech like precision ag, but also utilizing smarter designed and novel approaches to fuse the information that we're capturing from these platforms through AI. And we're moving into Industry 5.0, fully autonomous. And I just want to thank a lot of people I'm working with and lots of projects. And if, like I said, to stop my talk, I just want to say there's great opportunities for digital technologies in agriculture. If you see yourself working as a young student or young person working on long world-leading researches in UQ and across Australia to make a difference, especially in food security, food production. There's a Category 1 scholarship there that you can go to and read about that and also apply. Yeah, looking forward, and thank you for the opportunities again to the organizers, Sue and Zhang. Thank you for this, and yeah, thank you.
Well, thanks, Andries. So we got time for a few questions. So if you are online and you'd like to ask a question, either unmute yourself and just shout or raise your hand. So first we go to people online, and then, okay, Tree, please go ahead. If you unmute yourself, yeah, go ahead, yeah.
Hello, Fred, and hello, Associate Professor Su. I'm doing my research for information system for food safety. And then I'm very interested in your topic today because it's quite related to my PhD research. Also, I graduated 2 years ago. My research is related to how the information they can provide related to how the product from farm to table. And then during that time, whether what the farmer, they use the fertilizer and any chemicals, anything inside when they grow the plants, something like that. So that's why when I look, when I'm listening to your topic today, I'm quite interested in whether we can use AI to detect or to manage about anything from the soil, from the environment, maybe from the fertilizer we can use to tell the farmer that maybe this time we don't need to add too many fertilizer. I mean, next time we add more fertilizer. Or this time we can use this kind of chemical. Next time we don't use this kind of chemical, something like that. So that's just for the collaboration situation that we can consider only. No question, that's not the question, just something we can talk and discuss for further research on it. Thank you, Fred, and thank you, Sue.
Okay, thank you, Tree. Any other questions online for Andries? If not, then any question from the room? Is there anyone in the room? I can't see any, so if you let me, is there any?
Yeah, there's one, yeah.
Okay, go ahead, yeah.
I wonder if the audience can hear me. Fred?
Yeah, we can, yes.
Excellent, excellent. Okay, great. My name is Shazia Sadek, and I'd just like to start by thanking our speaker to coming and crossing the disciplinary sort of boundaries between agriculture and AI. Thank you very much for very inspiring talk and very important topics you touched upon. So my question is related to the quality of the data that is coming through the various sources that you have mentioned. So I know there is remote sensing, there is environmental sensors, there's some loggers out there, there's lots of imaging data. So please shed some light on your struggles with the quality of the data and the effort that is required before it can actually be plugged into the advanced analytical methods. Yes, thank you.
If the question is about the quality of the data that goes into the system, but also from the different platforms. Definitely, I mean, I think the remote sensing platforms and sensing platforms, specifically remote sensing, the satellites platforms, there's a lot of, like Google Earth Engine has opened the whole space in this by very easily, much easier downloading and acquire satellite data. And that's the satellite that we're using, like Sentinel-2, is for free. And it's every 5 days. There are other satellites. When I started this work 20 years ago, you know, the MODIS satellite was at 250 meter pixels. But you need to understand also that if you download data, you need to, cross your T's and dot your I's, so you need to double check that it actually makes sense. And as we go, it goes through a lot of different checks and balances for a specific region to make sure that the satellite data that we use actually is usable to then take it further into the data analysis part. The observed data is challenging. We design protocols across these validation sites beforehand to make sure that the sensors are used are the same. So, and then also the way the data is recorded is digitally. So we try to minimize the human error in when you collect this data. So yeah, but it's probably still one of the most challenging aspects of any research project and application specifically, because there's a huge pressure on you as scientists to actually deliver something that's robust and can be operationally used later on. So not just a theoretical analysis, but just make sure that it's robust enough and that the system is simple enough, but not too simple, that can be used in operational systems across global scales. Yep. So the question is about starting water. So the model that we're using, the biophysical model, is a little bit simpler model. And basically, it's simulated at the climate station level, then we aggregate up to a shire level, a regional scale. There was a study done in the 1990s by Professor Graham and other people using detailed models like APSIM or detailed dynamic crop models, which actually simulates more accurately the soil moisture in the whole profile. And for the application we're using it, not that the biophysics, just by simulating crop stress, that crop stress pattern due to water limitation is calibrated based on actual data. So those coefficients is actually calibrated, and we update that calibration every 5 years as we get more ABS. The actual data is ABS census data at the district level. Yes, but now we're moving into that space in terms of predicting field scale yield, which is a different question. The good thing about remote sensing is that the signal you get from the morphological aspect of how a canopy grows, and also the photosynthesis of that canopy, regardless of the crop, is actually already measured through the remote sensing bands at a very high resolution scale. So by knowing how the season is progressing from the crop stress model, biophysical model, and then incorporating the remote sensing signal, allows you then to outscale spatially the pattern, because the crop stress will be very similar at that farm or field scale due to the season. If it's dry, it's dry. If it rains, if it's flooding, it's flooding. There's some years in between that you won't pick it up correctly. For example, the crop stress model, or biophysical model, we some years that the farmers can't plant, we still simulate the signal of how a canopy or crop would grow under very high stress conditions. So yeah, obviously there's horses for courses, but using then also remote sensing to develop then and incorporate the soil moisture at start of the crop growing season definitely will improve the on-farm scalability of that. So you still have the overall signal of the impact of climate on that 5 by 5 kilometer or that farm, but then you use remote sensing from soil moisture and also from morphological and chlorophyll perspective to actually outscale that signal to a plant level and a canopy level more accurately.
Is there anyone in the room? Or if there's not, I would like to ask one high-level question that I always wanted to ask you, is that you've been using a lot of machine learning models for different purposes on different components of your pipeline and everything. Has there been, and you know, when we design a machine learning model, we simulate it on some, you know, simple data, and then we call it a success. But when you use it in real application, most often a lot of them fail. Has there been a machine learning model that you used in your application and you were so impressed, you said, okay, this is exactly what I wanted? Just keep just one.
Yeah.
Name one.
The machine learning model is exactly what I want.
Yeah.
Yeah, well, we're very excited about the approaches that we've derived now in this crop fam project in terms of predicting or discriminating between crops.
Do you have a specific method that you're?
Yeah, well, it's one that actually incorporates both. Well, there's still work to be done on the spatial adjacent, both maybe combining a CNN model with a LSTM model.
Okay.
A combinational image-based model with at the pixel scale with a temporal model, but the one that we're using currently is a temporal model. And yeah, I think there's still, we're not there yet, but you know, we've advanced tremendously in terms of having something that can be operationally applied. Okay. And obviously, from your work, you've seen some of the data. You know that there's always going to be hits and misses somewhere and some noise. Mainly, due to the model inaccuracy or calibration coefficients, but also, for example, if the coming winter season or summer season, you're experiencing climate environments that has never been seen before. So that response that the data was trained on has never been, is not included in the coming season. Sure. So then that's still a big challenge for, these deep learning models, I think. And then if it comes into, I've got some ideas around that about domain adaptation, in terms of including the environment. And, rather than say, oh, okay, domain adaptation, we just follow a pure mathematical approach. I would say, think about the way a crop is seeing and experiencing climate and then biophysically, how that will then play out in a new environment that has never been seen before. And that's the power of crop modeling. If you link crop modeling with your machine learning, that is very powerful. And we've seen it now with the GCM, just by linking a GCM, which is not a machine learning model, but it's a Bayesian downscaling approach. I'd like to talk to you about that at the later stage too, but yeah. So yeah, I can't say. I think the thing is to have something that's operationally applicable and can be deployed. It's one thing to have a very accurate model. You can be 99% accurate, but if you can't deploy it in a system, it's probably no utility to the industry.
Fair enough. All right, I think thanks a lot, Andries. I think we're over time a little bit. So thank you so much, everyone. Thank you for coming, and thanks, Andries. Remember, we have another talk on the same theme in May.
Okay, Matt. Thank you. Right. See you, Fred. Thank you.
See you, everyone.